Hi everyone. So recently I gave a 30-minute talk on large language models, just kind of like an intro talk. Unfortunately, that talk was not recorded, but a lot of people came to me after the talk and they told me that they really liked the talk. So I thought I would just re-record it and basically put it up on YouTube. So here we go, the busy person's intro to large language models, director's cut. Okay, so let's begin. First of all, what is a large language model really? Well, a large language model is just two files, right? There will be two files in this hypothetical directory. So for example, working with the specific example of the Llama 2 70B model, this is a large language model released by Meta AI. And this is basically the Llama series of language models, the second iteration of it. And this is the 70 billion parameter model of this series. So there's multiple models belonging to the Llama 2 series, 7 billion, 13 billion, 34 billion, and 70 billion is the biggest one. Now, many people like this model specifically because it is probably today the most powerful open weights model. So basically the weights and the architecture and a paper was all released by Meta. So anyone can work with this model very easily by themselves. This is unlike many other language models that you might be familiar with. For example, if you're using ChatGPT or something like that, the model architecture was never released. It is owned by OpenAI, and you're allowed to use the language model through a web interface, but you don't have actually access to that model. So in this case, the Llama 2 70B model is really just two files on your file system, the parameters file and the run, some kind of a code that runs those parameters. So the parameters are basically the weights or the parameters of this neural network that is the language model. We'll go into that in a bit. Because this is a 70 billion parameter model, every one of those parameters is stored as 2 bytes. And so therefore, the parameters file here is 140 gigabytes. And it's 2 bytes because this is a float 16 number as the data type. Now, in addition to these parameters, that's just like a large list of parameters for that neural network. You also need something that runs that neural network. And this piece of code is implemented in our run file. Now, this could be a C file or a Python file or any other programming language, really. It can be written in any arbitrary language, but C is sort of like a very simple language, just to give you a sense. And it would only require about 500 lines of C with no other dependencies to implement the neural network architecture and that uses basically the parameters to run the model. So it's only these two files. You can take these two files and you can take your MacBook. And this is a fully self-contained package. This is everything that's necessary. You don't need any connectivity to the internet or anything else. You can take these two files, you compile your C code, you get a binary that you can point at the parameters, and you can talk to this language model. So for example, you can send it text, like for example, write a poem about the company Scale AI, and this language model will start generating text. And in this case, it will follow the directions and give you a poem about Scale AI. Now, the reason that I'm picking on Scale AI here, and you're going to see that throughout the talk, is because the event that I originally presented this talk with was run by Scale AI. And so I'm picking on them throughout the slides a little bit, just in an effort to make it concrete. So this is how we can run the model. It just requires two files, just requires a MacBook. I'm slightly cheating here because this was not actually, in terms of the speed of this video here, this was not running a 70 billion parameter model. It was only running a 7 billion parameter model. A 70B would be running about 10 times slower, but I wanted to give you an idea of sort of just the text generation and what that looks like. So not a lot is necessary to run the model. This is a very small package, but the computational complexity really comes in when we'd like to get those parameters. So how do we get the parameters and where are they from? Because whatever's in the run.c file, the neural network architecture and sort of the forward pass of that network, everything is algorithmically understood and open and so on. But the magic really is in the parameters and how do we obtain them? So to obtain the parameters, basically the model training, as we call it, is a lot more involved than model inference, which is the part that I showed you earlier. So model inference is just running it on your MacBook. Model training is a computationally very involved process. So basically what we're doing can best be sort of understood as kind of a compression of a good chunk of internet. So because Llama 2 70B is an open source model, we know quite a bit about how it was trained because Meta released that information in a paper. So these are some of the numbers of what's involved. You basically take a chunk of the internet that is roughly, you should be thinking 10 terabytes of text. This typically comes from like a crawl of the internet. So just imagine just collecting tons of text from all kinds of different websites and collecting it together. So you take a large chunk of internet, then you procure a GPU cluster. These are very specialized computers intended for very heavy computational workloads like training of neural networks. You need about 6,000 GPUs, and you would run this for about 12 days to get a Llama 2 70B. And this would cost you about $2 million. And what this is doing is basically it is compressing this large chunk of text into what you can think of as a kind of a zip file. So these parameters that I showed you in an earlier slide are best kind of thought of as like a zip file of the internet. And in this case, what would come out are these parameters, 140 gigabytes. So you can see that the compression ratio here is roughly like 100x, roughly speaking. But this is not exactly a zip file because a zip file is lossless compression. What's happening here is a lossy compression. We're just kind of like getting a kind of a gestalt of the text that we trained on. We don't have an identical copy of it in these parameters. And so it's kind of like a lossy compression. You can think about it that way. The one more thing to point out here is these numbers here are actually, by today's standards in terms of state-of-the-art, rookie numbers. So if you want to think about state-of-the-art neural networks, like say what you might use in ChatGPT or Claude or Bard or something like that, these numbers are off by a factor of 10 or more. So you would just go in and you would just like start multiplying by quite a bit more. And that's why these training runs today are many tens or even potentially hundreds of millions of dollars, very large clusters, very large data sets. And this process here is very involved to get those parameters. Once you have those parameters, running the neural network is fairly computationally cheap. Okay, so what is this neural network really doing, right? I mentioned that there are these parameters. This neural network basically is just trying to predict the next word in a sequence. You can think about it that way. So you can feed in a sequence of words, for example, cat sat on A. This feeds into a neural net, and these parameters are dispersed throughout this neural network. And there's neurons, and they're connected to each other, and they all fire in a certain way. You can think about it that way. And out comes a prediction for what word comes next. So for example, in this case, this neural network might predict that in this context of 4 words, the next word will probably be Matt with, say, 97% probability. So this is fundamentally the problem that the neural network is performing. And this, you can show mathematically that there's a very close relationship between prediction and compression, which is why I sort of allude to this neural network as a kind of training it as kind of like a compression of the internet. Because if you can predict sort of the next word very accurately, you can use that to compress the data set. So it's just a next word prediction neural network. You give it some words, it gives you the next word. Now, the reason that what you get out of the training is actually quite a magical artifact is that basically the next word prediction task you might think is a very simple objective, but it's actually a pretty powerful objective because it forces you to learn a lot about the world inside the parameters of the neural network. So here I took a random web page at the time when I was making this talk. I just grabbed it from the main page of Wikipedia, and it was about Ruth Handler. And so think about being the neural network, and you're given some amount of words and trying to predict the next word in a sequence. Well, in this case, I'm highlighting here in red some of the words that would contain a lot of information. And so, for example, if your objective is to predict the next word, presumably your parameters have to learn a lot of this knowledge. You have to know about Ruth and Handler and when she was born and when she died, who she was, what she's done, and so on. And so in the task of next word prediction, you're learning a ton about the world, and all this knowledge is being compressed into the weights, the parameters. Now, how do we actually use these neural networks? Well, once we've trained them, I showed you that the model inference is a very simple process. We basically generate what comes next. We sample from the model, so we pick a word, and then we continue feeding it back in and get the next word and continue feeding that back in. So we can iterate this process, and this network then dreams internet documents. So for example, if we just run the neural network, or as we say, perform inference, we would get sort of like web page dreams. You can almost think about it that way, right? Because this network was trained on web pages, and then you can sort of like let it loose. So on the left, we have some kind of a Java code dream, it looks like. In the middle, we have some kind of what looks like almost like an Amazon product dream. And on the right, we have something that almost looks like a Wikipedia article. Focusing for a bit on the middle one as an example, The title, the author, the ISBN number, everything else, this is all just totally made up by the network. The network is dreaming text from the distribution that it was trained on. It's just mimicking these documents. But this is all kind of like hallucinated. So for example, the ISBN number, this number probably, I would guess almost certainly does not exist. The model network just knows that what comes after ISBN colon is some kind of a number of roughly this length, and it's got all these digits. And it just like puts it in. It just kind of like puts in whatever looks reasonable. So it's parroting the training dataset distribution. On the right, the black-nosed dace, I looked it up, and it is actually a kind of fish. And what's happening here is this text verbatim is not found in a training set documents, but this information, if you actually look it up, is actually roughly correct with respect to this fish. And so the network has knowledge about this fish. It knows a lot about this fish. It's not going to exactly parrot documents that it saw in the training set, but again, it's some kind of a lossy compression of the internet. It kind of remembers the gestalt, it kind of knows the knowledge, and it just kind of like goes and it creates the form. It creates kind of like the correct form and fills it with some of its knowledge. And you're never 100% sure if what it comes up with is, as we call, hallucination, or like an incorrect answer, or like a correct answer necessarily. So some of this stuff could be memorized, and some of it is not memorized, and you don't exactly know which is which. But for the most part, this is just kind of like hallucinating or like dreaming internet text from its data distribution. Okay, let's now switch gears to how does this network work? How does it actually perform this next word prediction task? What goes on inside it? Well, this is where things complicate a little bit. This is kind of like the schematic diagram of the neural network. If we kind of like zoom in into the toy diagram of this neural net. This is what we call the transformer neural network architecture, and this is kind of like a diagram of it. Now, what's remarkable about these neural nets is we actually understand in full detail the architecture. We know exactly what mathematical operations happen at all the different stages of it. The problem is that these 100 billion parameters are dispersed throughout the entire neural network. And so basically, these billions of parameters are throughout the neural net. And all we know is how to adjust these parameters iteratively to make the network as a whole better at the next word prediction task. So we know how to optimize these parameters. We know how to adjust them over time to get a better next word prediction. But we don't actually really know what these 100 billion parameters are doing. We can measure that it's getting better at the next word prediction, but we don't know how these parameters collaborate to actually perform that. We have some kind of models that you can try to think through on a high level for what the network might be doing. So we kind of understand that they build and maintain some kind of a knowledge database, but even this knowledge database is very strange and imperfect and weird. So a recent viral example is what we call the reversal curse. So as an example, if you go to ChatGPT and you talk to GPT-4, the best language model currently available, you say, who is Tom Cruise's mother? It will tell you it's Marilee Pfeiffer, which is correct. But if you say, who is Marilee Pfeiffer's son? It will tell you it doesn't know. So this knowledge is weird and it's kind of one-dimensional. And you have to sort of like, this knowledge isn't just like stored and can be accessed in all the different ways. You have to sort of like ask it from a certain direction almost. And so that's really weird and strange. And fundamentally, we don't really know because all you can kind of measure is whether it works or not and with what probability. So long story short, think of LLMs as kind of like mostly inscrutable artifacts. They're not similar to anything else you might build in an engineering discipline. Like they're not like a car where we sort of understand all the parts. They're these neural nets that come from a long process of optimization. And so we don't currently understand exactly how they work, although there's a field called interpretability or mechanistic interpretability, trying to kind of go in and try to figure out like what all the parts of this neural net are doing. And you can do that to some extent, but not fully right now. But right now we kind of treat them mostly as empirical artifacts. We can give them some inputs and we can measure the outputs. We can basically measure their behavior. We can look at the text that they generate in many different situations. And so I think this requires basically correspondingly sophisticated evaluations to work with these models because they're mostly empirical. So now let's go to how we actually obtain an assistant. So far, we've only talked about these internet document generators, right? And so that's the first stage of training. We call that stage pre-training. We're now moving to the second stage of training, which we call fine-tuning. And this is where we obtain what we call an assistant model. Because we don't actually really just want document generators. That's not very helpful for many tasks. We want to give questions to something, and we want it to generate answers based on those questions. So we really want an assistant model instead. And the way you obtain these assistant models is fundamentally through the following process. We basically keep the optimization identical, so the training will be the same. It's just the next word prediction task, but we're going to swap out the data set on which we are training. So it used to be that we are trying to train on internet documents. We're going to now swap it out for data sets that we collect manually. And the way we collect them is by using lots of people. So typically a company will hire people and they will give them labeling instructions, and they will ask people to come up with questions and then write answers for them. So here's an example of a single example that might basically make it into your training set. So there's a user, and it says something like, can you write a short introduction about the relevance of the term monopsony in economics, and so on. And then there's assistant, and again, the person fills in what the ideal response should be. And the ideal response and how that is specified and what it should look like, it all just comes from labeling documentations that we provide these people. And the engineers at a company like OpenAI or Anthropic or whatever else will come up with these labeling documentations. Now, the pre-training stage is about a large quantity of text, but potentially low quality because it just comes from the internet and there's tens of or hundreds of terabyte of it, and it's not all very high quality. But in this second stage, we prefer quality over quantity. So we may have many fewer documents, for example, 100,000, but all of these documents now are conversations, and they should be very high quality conversations, and fundamentally people create them based on labeling instructions. So we swap out the data set now, and we train on these Q&A documents. And this process is called fine-tuning. Once you do this, you obtain what we call an assistant model. So this assistant model now subscribes to the form of its new training documents. So for example, if you give it a question, like, can you help me with this code? It seems like there's a bug, print hello world. Even though this question specifically was not part of the training set, the model, after its fine-tuning, understands that it should answer in the style of a helpful assistant to these kinds of questions. And it will do that. So it will sample word by word again, from left to right, from top to bottom, all these words that are the response to this query. And so it's kind of remarkable and also kind of empirical and not fully understood that these models are able to sort of like change their formatting into now being helpful assistants because they've seen so many documents of it in the fine-tuning stage, but they're still able to access and somehow utilize all of the knowledge that was built up during the first stage, the pre-training stage. So roughly speaking, pre-training stage is trains on a ton of internet and is about knowledge. And the fine-tuning stage is about what we call alignment. It's about sort of giving, it's about like changing the formatting from internet documents to question and answer documents in kind of like a helpful assistant manner. So roughly speaking, here are the two major parts of obtaining something like ChatGPT. There's the stage 1 pre-training and stage 2 fine-tuning. In the pre-training stage, you get a ton of text from the internet. You need a cluster of GPUs. So these are special purpose computers for these kinds of parallel processing workloads. This is not just things that you can buy in Best Buy. These are very expensive computers. And then you compress the text into this neural network, into the parameters of it. Typically, this could be a few millions of dollars. And then this gives you the base model. Because this is a very computationally expensive part, this only happens inside companies maybe once a year or once after multiple months, because this is kind of like very expensive to actually perform. Once you have the base model, you enter the fine-tuning stage, which is computationally a lot cheaper. In this stage, you write out some labeling instructions that basically specify how your assistant should behave. Then you hire people. So for example, Scale AI is a company that actually would work with you to actually basically create documents according to your labeling instructions. You collect 100,000, as an example, high quality, ideal Q&A responses. And then you would fine-tune the base model on this data. This is a lot cheaper. This would only potentially take like 1 day or something like that instead of a few months or something like that. And you obtain what we call an assistant model. Then you run a lot of evaluations, you deploy this, and you monitor, collect misbehaviors. And for every misbehavior, you want to fix it. And you go to step 1 and repeat. And the way you fix the misbehaviors, roughly speaking, is you have some kind of a conversation where the assistant gave an incorrect response. So you take that and you ask a person to fill in the correct response. And so the person overwrites the response with the correct one, and this is then inserted as an example into your training data. And the next time you do the fine-tuning stage, the model will improve in that situation. So that's the iterative process by which you improve this. Because fine-tuning is a lot cheaper, you can do this every week, every day, or so on. And companies often will iterate a lot faster on the fine-tuning stage instead of the pre-training stage. One other thing to point out is, for example, I mentioned the Llama 2 series. The Llama 2 series actually, when it was released by Meta, contains both the base models and the assistant models. So they release both of those types. The base model is not directly usable because it doesn't answer questions with answers. If you give it questions, it will just give you more questions, or it will do something like that because it's just an internet document sampler. So these are not super helpful. Where they are helpful is that Meta has done the very expensive part of these two stages. They've done the stage one and they've given you the result. And so you can go off and you can do your own fine-tuning. And that gives you a ton of freedom. But Meta, in addition, has also released assistant models. So if you just like to have a question answer, you can use that assistant model and you can talk to it. Okay, so those are the two major stages. Now see how in stage 2 I'm saying and or comparisons? I would like to briefly double click on that because there's also a stage 3 of fine-tuning that you can optionally go to or continue to. In stage 3 of fine-tuning, you would use comparison labels. So let me show you what this looks like. The reason that we do this is that in many cases, it is much easier to compare candidate answers than to write an answer yourself if you're a human labeler. So consider the following concrete example. Suppose that the question is to write a haiku about paperclips or something like that. From the perspective of a labeler, if I'm asked to write a haiku, that might be a very difficult task, right? Like I might not be able to write a haiku. But suppose you're given a few candidate haikus that have been generated by the assistant model from stage 2. Well, then as a labeler, you could look at these haikus and actually pick the one that is much better. And so in many cases, it is easier to do the comparison instead of the generation. And there's a stage 3 of fine-tuning that can use these comparisons to further fine-tune the model. And I'm not going to go into the full mathematical detail of this. At OpenAI, this process is called reinforcement learning from human feedback, or RLHF. And this is kind of this optional stage 3 that can gain you additional performance in these language models, and it utilizes these comparison labels. I also wanted to show you very briefly one slide showing some of the labeling instructions that we give to humans. So this is an excerpt from the paper InstructGPT by OpenAI. And it just kind of shows you that we're asking people to be helpful, truthful, and harmless. These labeling documentations, though, can grow to tens or hundreds of pages and can be pretty complicated. But this is roughly speaking what they look like. One more thing that I wanted to mention is that I've described the process naively as humans doing all of this manual work, but that's not exactly right, and it's increasingly less correct. And that's because these language models are simultaneously getting a lot better, and you can basically use human-machine sort of collaboration to create these labels with increasing efficiency and correctness. And so, for example, you can get these language models to sample answers, and then people sort of like cherry pick parts of answers to create one sort of single best answer. Or you can ask these models to try to check your work, or you can try to ask them to create the comparisons, and then you're just kind of like in an oversight role over it. So this is kind of a slider that you can determine, and increasingly these models are getting better. We're moving the slider sort of to the right. Okay, finally, I wanted to show you a leaderboard of the current leading large language models out there. So this, for example, is the chatbot arena. It is managed by a team at Berkeley. And what they do here is they rank the different language models by their ELO rating. And the way you calculate ELO is very similar to how you would calculate it in chess. So different chess players play each other, and depending on the win rates against each other, you can calculate their ELO scores. You can do the exact same thing with language models. So you can go to this website, you enter some question, you get responses from two models, and you don't know what models they were generated from, and you pick the winner. And then depending on who wins and who loses, you can calculate the ELO scores. So the higher, the better. So what you see here is that crowding up on the top, you have the proprietary models. These are closed models. You don't have access to the weights. They are usually behind a web interface. And this is GPT series from OpenAI and the Claude series from Anthropic. And there's a few other series from other companies as well. So these are currently the best performing models. And then right below that, you are going to start to see some models that are open weights. So these weights are available. A lot more is known about them. There are typically papers available with them. And so this is, for example, the case for Llama 2 series from Meta. Or on the bottom, you see Zephyr 7B beta. That is based on the Mistral series from another startup in France. But roughly speaking, what you're seeing today in the ecosystem is that the closed models work a lot better, but you can't really work with them, fine-tune them, download them, etc. You can use them through a web interface. And then behind that are all the open source models and the entire open source ecosystem. And all of this stuff works worse, but depending on your application, that might be good enough. And so currently, I would say the open source ecosystem is trying to boost performance and sort of chase the proprietary ecosystems. And that's roughly the dynamic that you see today in the industry. Okay, so now I'm going to switch gears and we're going to talk about the language models, how they're improving, and where all of it is going in terms of those improvements.